James Jones, Weather Emissions and Outdoor Air Pollution Implications of Climate Change.
Okay, hello everybody. I'm really excited to talk about this project that I've been working on for some time that kind of generally tries to think about the implications of climate change on outdoor air pollution and tries to uncover some of the mechanisms behind that to give us some insight about our ability to mitigate those impacts. This is largely motivated by the observed relationship between high temperatures and poor air quality. So what I'm showing you here are two scatter plots of ozone pollution on the left-hand side and fine particulate matter on the right-hand side and their relationship with maximum daily temperatures in the US. And you can see, especially for ozone, you have a very tight relationship with high temperatures where ozone pollution increases or tends to be associated with very high ozone levels tend to be observed on very, very warm days. And the relationship is somewhat more mixed for fine particulate matter, but we might worry that to extent that there's some causal mechanism here that a warming climate could further exacerbate outdoor air pollution issues. And the main focus on what I'm looking at is trying to pull apart this relationship into essentially what I think of as two components, a direct kind of impact that's related to sort of changes in the physical system that drive poor air quality. For example, with ozone pollution, the process that results in the formation of ozone pollution is heavily dependent on high temperatures. So we can imagine that there might be a direct channel where high temperatures cause changes to this physical system that exacerbates air quality issues. But there might also be indirect channels through changes in human behavior. For example, if humans are increasing, say, electricity use to run air conditioners more intensively in response to extreme heat, you could see an increase in pollution emissions that could exacerbate air quality issues. And the relative importance of these two channels has important implications for how we think about mitigating these impacts. You could imagine a world where this is primarily driven by this direct channel, this change in the physical system, and that would indicate there's relatively little we can do on the side to reduce anthropogenic emissions if this is all acting through changes in the physical system. Whereas if it mostly works through this indirect channel, it's somewhat encouraging in the sense that we could, in theory, at least conceptually, try to modify human behavior in these anthropogenic systems to try to break this linkage. And so what I do is essentially two pieces. First is to start to investigate this indirect channel and essentially ask, how do pollution emissions in the US power sector respond to extreme temperatures? Electricity use has been demonstrated to very closely respond to extreme high and low temperatures, and it's plausible to think that this could pass through into pollution emissions. And I'll show you that, in response to extremely hot and extremely cold temperatures, generating units come online and produce more NOx emissions than they would have otherwise in mild temperatures. And in a simple scenario analysis, you can see that aggregate NOx emissions increase by roughly 1.6% for a 2 degrees Celsius increase and almost 8% for a 5 degrees Celsius increase. And then the second piece tries to look at the downstream impact of this to understand how this indirect channel of increased emissions can lead to poor air quality, and tries to think about to what extent is this direct versus indirect effect. And I'll show you that for a very large 5 degrees Celsius increase, ozone and particulate matter levels increase, and that this is, at least for ozone, primarily this direct effect, whereas for particulate matter it's somewhat more mixed. So in the time I have, I'll try and give you a sense of what I'm doing here. So this first piece looks at how pollution emissions in the power sector respond to extreme temperatures, and it uses some high-frequency data on electricity generators together with fine-scale weather data from the PRISM group. And essentially I'm running a Heckman selection model where we're thinking about how do, in the first stage, how do temperatures influence the probability that a generator is on or off on any given day. And then the second stage, conditional on the generator being on, how do high temperatures influence the quantity of NOx emissions that are produced at this plant? So this research design focuses on exploiting a year-to-year variability in weather, using essentially each generator as its own treatment and control to try to trace out kind of a causal effect of changes in atmospheric conditions and temperatures on pollution emissions. And so this is essentially the average marginal effect of these different temperature variables on pollution emissions, because in this model you essentially have two effects. One effect is that on an extremely hot day a generator could be induced to turn on or turn off, and then you also have an effect of the quantity of emissions that it produces. I segment generators based on the fuel they use, and use a clustering process to group together generators of similar size and ages to try to identify different types of effects across generators. So what you can see is that for some generators, they are very highly responsive to extreme temperatures, and whereas for other generators, it's much more limited. And to see this in a more, in an alternative way, so this is a simple scenario analysis where I think about if you were to uniformly increase temperatures by some fixed amount across the US and predict the changes in aggregate NOx emissions from all of these generating units, you can see that with a milder winter, NOx emissions fall during the winter periods and increase during the summer. And then the next piece of this is trying to look at essentially the downstream effects of this. That can we try to disentangle the two effects of atmospheric conditions and temperatures from this indirect effect of NOx emissions, anthropogenic activity. So this uses a model where I'm essentially predicting the quantity of either ozone or particulate matter at a monitoring site as a function of several weather variables, as well as the emissions from power plants in the surrounding area. The idea being that we identify this effect of extreme temperatures using variability in weather at the monitoring site, and then use variability from emissions in the surrounding area to try to identify the effect of pollutant emissions. And it uses a relatively simple process to link emissions from surrounding areas to monitoring sites that takes advantage of variation in the direction of the wind. So if we can think of a scenario where you have a monitoring site in the middle and 3 polluting facilities surrounding it, if each of these facilities produces emissions of this magnitude with the wind blowing in this particular direction, then if we calculate this angle between the direction of the wind and the direction of the monitor, then we can say that this proportion of emissions gets blown in the direction of the monitoring site. And so I aggregate these directionally adjusted emissions across different distance bands to try to link emissions in the surrounding area to the monitoring site. And so the results look somewhat like this. This looks at the relative change of ozone levels in response to daily maximum temperature relative to the 18 to 21 degrees Celsius level. In all of these regions, you can see a high sensitivity to extreme temperatures, though in some cases you see this an increase in ozone levels in response to extremely cold temperatures, which in part could be some issues with the model picking up other sources of anthropogenic emissions. For example, if people are heating their homes with natural gas or kerosene, to the extent that that responds to extremely cold temperatures, that would start to get picked up here. And this is somewhat more apparent for particulate matter. You can see that particulate matter levels appear to be responding both to extremely high and extremely low temperatures. And so in terms of emissions, so for in this kind of framework, the effect of pollution emissions on pollution concentrations was a function of the distance between the two. And so this figure plots out the effect of a 1 standard deviation increase in NOx emissions at various distances. And in general, you can see that the estimates are somewhat mixed across regions, and but for many regions, we do seem to be picking up some positive impact of NOx emissions on ozone, and the same holds for particulate matter. And so to try to put these together, I use a simple kind of scenario analysis where I think about, so in this framework, an increase in temperatures has 2 effects. One, it increases temperatures directly at the monitoring site, and that effect gets picked up through this temperature response function. And it has this indirect effect of increasing NOx emissions in the surrounding areas, which works through this emissions response function. And I perform a simple scenario analysis where I increase the temperatures and allow the model to work through either one of the 2 channels. And so in the top right, I'm essentially simulating a 5 degrees Celsius increase, but only letting it work through this indirect channel of NOx emissions. And you can see the change in ozone levels relative to a baseline of no change in temperatures. And you see a very relatively small increase in average ozone levels over the summer period. Whereas if you do the opposite, increasing temperatures, but holding this NOx channel fixed, you see a relatively larger impact, especially during the summer year. And these two combine them together. So the kind of the conclusion from here is that what's primarily driving this result is essentially this direct channel versus this indirect channel of NOx emissions. Whereas the two for particulate matter are more similar in magnitude, but still primarily dominated by this direct channel. And so that's essentially what I've been working on, and I suppose the implication of this would be that if this is primarily working through a direct channel, through a change in atmospheric conditions as opposed to changes in anthropogenic emissions, it might be potentially very challenging to reduce or to mitigate this impact, as you might need a potentially very large reduction in NOx emissions in order to compensate for the increase in temperatures. So, thank you.
So we've got time for a couple of questions. I just wanted to point out that up in the very top there, CEEP is the Center for Environmental Economics and Policy. Its director is over here, Wolfram Flenker, and it's located at SEPA, and that's what that stands for.
Maybe I was distracted and didn't pay enough attention. Could you tell us a bit more about the source of your data,
Okay.
the scope of the information, how this data set is going to grow in the future?
Yeah, sorry, I tried to get to what I could discuss in the time. So in terms of emissions and weather, this is largely driven by the EPA Air Markets Program data set, which is a high-frequency data set, essentially hourly data for almost all the fossil fuel generators in the United States, where each hour generators report whether they're on or off, and then NOx, SO2, and carbon dioxide emissions for each hour of the day. And I couple this together with daily temperature and precipitation data from the PRISM group. How this data will grow in the future, this continues to be collected, and the data set continues to expand as time goes.
I had a question too. So could you in principle just predict the change in the probability of counties getting into non-attainment, because you have this relationship between higher temperatures and...
Yeah. So I didn't have a chance to talk about that today, but for ozone pollution, I think in a 5 degrees Celsius kind of scenario, the probability of exceeding the current federal standard roughly triples, and then for particulate matter, the probability of exceeding the short-term standard roughly quadruples. What I have right here.
Okay, thank you.